Distinguished experts, colleagues, and members of the academic committee, good afternoon. I'm Zhao from the University of Nottingham, Ningbo, China. Today, it's my distinct privilege to present my latest breakthrough in microsatellite communications, a self-deploying high-gain eternal mechanism enabled by ship memory polymer composites, or SMPCs material. This work is not merely about folding an tunnel. It's about resolving a fundamental engineering paradox: how to extract large-scale capability from the volumetric confinement of a CubeSats using the intelligence of materials rather than the complexity of machines. The democratization of space has fundamentally altered our industry. CubeSats, once regarded as educational novelties, have matured into capable platforms for deep space exploration and high-resolution remote sensing. However, as we push these platforms further, we encounter a barrier imposed by physics. High data rates demand high gain, and high gain mandates large internal apertures. Current state-of-the-art solutions, such as the deployable mesh reflectors used the unnecessary cube mention or the folded panels on Marco, rely heavily on complex metal hinges, motors, and springs. While effective, these traditional electromechanical architectures impose severe penalties. Research indicates they can consume over 20% of a satellite's mass budget and introduce critical failure modes, such as code whitening and mechanical jamming in the volume of space. Our challenge was clear: how do we reliably store a 0.5 meter aperture into a 1.5 U volume, a space roughly the size of a carton of milk, and guarantee its deployment without heavy actuators? Our solution is a paradigm shift we call material as machine. We have systematically replaced the traditional motors and gears with carbon fiber-reinforced ship memory polymer composites. Unlike ship memory alloys, which are typically limited to roughly 8% recoverability strain, our optimized SMPCs material achieve recoverability strengths of severe 100%. The operational concept is elegant in its simplicity. On Earth, we fold the antenna and heat it above its glass transition temperature to lock it into a temporary, compact geometry. In orbit, simple resistive heating triggers the material to release its stored elastic potential energy, automatically driving the structure back to its preset parabolic form. This process eliminates the need for motors and transmission gears entirely, significantly enhancing system reliability by reducing the parts count. To manage the complex geometry of a parabolic dish, we turn to the mathematics of origami. We selected the Miura-Ori folding pattern for two strategic reasons. First, it enables a storage ratio exceeding 8:1, allowing us to pack a meter-scale structure into a normal satellite form factor. Second, and perhaps more importantly, the Miura-Ori pattern possesses a single degree of freedom deployment characteristic. This means the deployment path is kinematically determinate. The structure has only one way to open. This drastically reduces the stochastic risk of entanglement common in net-based tunnels. To address the inherent flexibility of thin films, we integrated a lightweight SMPC material truss structure that co-folds with the membrane, providing the necessary structural stiffness and surface accuracy required for high-frequency Ka-band communications. However, the controlled release of elastic energy in microgravity can be catastrophic. To prevent the internal petals from colliding or generating excessive mechanical shock, which could disturb the satellite's attitude, we engineered a gradient response deployment system. By varying the heating rates and actuation temperatures across different hinge sites, we can choreograph the deployment sequence. Outer hinges are designed to actuate first, followed by the inner layers. Ground testing confirms that this staged process completes smoothly with 120 seconds. This controlled release completely avoids the instantaneous high shock impact typical of spring-loaded release mechanisms, protecting sensitive onboard instruments. Deployment is only half the battle. Ship retention is equally critical. Once the heating ceases, The SMPC material cools below its glass transition temperature and undergoes vitrification. The material modulus recreases sharply, providing a passive lock at the molecular level. To ensure absolute mission assurance, we integrated secondary ship membrane alloy latches at key structural nodes. This dual locking mechanism, combining material vitrification with mechanical latching, ensures the tunnel maintains a high-precision parabolic configuration even during rapid attitude maneuvers or thermal cycling of eclipse periods. In the extreme thermal environment of orbit, materials expand and contract. For a Ka band tunnel operating at 35.75 GSA, even micro-level thermal deformations can severely degrade gain. We address this by designing a specialized honeycomb backing structure. Through topological optimization, this structure exhibits negative thermal expansion properties. As the reflector material expands under solar heating, the backing structure mechanically contracts, passively neutralizing the thermal deformation. Furthermore, we embedded SMA micro actuators for active error correction. This hybrid active-passive strategy ensures RF stability throughout the satellite's operational lifecycle. For beam pointing, we avoided the weight penalty of traditional motorized gimbals. Instead, we developed a hybrid manipulation system. For cross-pointing adjustments of plus or minus degrees, we utilize SMPC material-driven universal joint. For high-frequency jitter correction and rapid beam switching, we integrated an electronic-based array feed. This mechanical plus electronic architecture allows us to retain the lightweight advantage of SMPCs material while delivering the agility of a paced array. It represents an ideal compromise between SWAP constraints and performance. To validate this design, we manufactured a high-fidelity prototype using precision autoclave molding. We selected a cyanide ester-based SMPC material capable of operating at 210 degrees Celsius. By optimizing the Q cycle ranging between 150 to 200 degrees Celsius at 0.7 ampere, we successfully controlled the void content to below 2%. This low porosity is critical. It ensures robust mechanical properties and meets the ultra-low outgassing requirements essential for preventing sensor contamination in space. Reliability is the currency of space exploration. Our prototype underwent rigorous ground qualification consistent with NASA standards. We conducted random vibration testing to simulate the acoustic loads of launch and thermal vacuum cycling to replicate the harsh orbital environment. The results were conclusive. Even after 140 long cycles, the SMPC material hinges maintained consistent covering rates, with no evidence of structural fatigue. This data provides high confidence that the mechanism can withstand the rigors of launch and operation. When benchmarked against state-of-the-art missions, the advantages of our design become distinct. Compared to the ring-cube mechanical mesh tunnel, our SMPC material design achieves a higher storage ratio of more than 8:1 and reduces system mass by approximately 40% by eliminating heavy motors. Compared to the macro reflector array, we achieved higher gain within a smaller storage footprint. This confirms that SMPC material-based architectures offer superior competitiveness in terms of mass, volume, and performance. Building on our ground success, we have defined a clear path for on-orbit verification. Upon orbit insertion and determinably, the flight computer will trigger the resistive heating sequence. We will monitor current draw to confirm the pace transition. Once deployed, the satellite will establish a Ka-band link, allowing us to invert the retrieved signal strength to calculate the actual tunnel gain and pointing accuracy. This will mark the final transition from technology demonstration to operational capability. In conclusion, this research has successfully designed, manufactured, and verified a self-deploying high-gain tunnel driven by intelligent materials. We have not only solved a specific pack engine engineering problem, but have also demonstrated a design philosophy of smart structures. This technology paves the way for future deep space CubeSat constellations and high-throughput Earth observation. We believe that as material science advances, microsatellites will soon rival the communication capabilities of their larger counterparts. Thank you for your attention.